Good morning. In the last lecture we started talking about separations, which is a classical traditional mechanical operation, and we said that initially we will focus on mechanical separations, and so there are three in particular that we will discuss. The first one was screening / sieving, the second was filtration, and the third was sedimentation. And in the last lecture we looked at how screens operate, how you define the effectiveness of a screen, the capacity of a screen, and so on. So in this class we will next discuss filtration as a mechanism for separation. So a filter is used to separate a typically a particle or a chemical vapor from a carrier fluid, which can be a gas or a liquid. So there are basically two types of filters, gas filters and liquid filters, and there are two types of filtrates. You can try to filter chemical species, in which case you may have to use chemisorption as a mechanism, or you can try to separate particles, in which case you can use simple mechanical separators for achieving that. So again, we will focus this discussion on the separation of solid particles from gaseous and liquid media. Another classification is the purpose for the filtration. There are two major purposes. The first is analysis. Sometimes you want to remove particles from a fluid stream in order to analyze them, characterize them for size, shape, structure, chemical properties, functional properties, and so on. So in that case, the primary purpose is analysis, where you don't care if the process of separation is reversible or irreversible. You just want to be able to remove the particles from the fluid and have them available for subsequent analysis. The second purpose, of course, is purification, and commercially speaking, that has much wider application. You are constantly purifying gases, purifying liquids. You know, I am sure many of you have water purifiers at home. I am sure your hostels have water purifiers. They all operate on the principle of filtration, in addition to, of course, other purification mechanisms as well. So that is another way of classifying. The other way of classifying is coarse versus fine. Coarse particles are filtered in a very different way compared to fine particles. So typically a coarse particle filter can be simply a fabric filter. You can just stretch a fabric, make the gas or liquid go through it. It is more like a strainer rather than a filter. There are also what are called granular bed filters, where you have a bed that consists of, that provides a path, a tortuous path for the fluid to go through, and as it does, the bed materials, typically it could be just pebbles, sand, whatever, removes impurities from the fluid. Another example are electrostatic precipitators. You know, particularly in power plants where you have coal as the fuel, you generate a large amount of fly ash, and these fly ash particles need to be collected, and they can actually be put to commercial use, but first they have to be collected. And electrostatic precipitators are widely used for this purpose, and they, you know, as the name suggests, they use a static electrostatic field as the collection mechanism. Now if you look at fine particle separation, there are two types of filters, fibrous and membrane, and it is important to understand some of the key differences between the two, both in terms of how they are fabricated as well as again their primary properties. So let us just make a little table. So the first thing you have to realize is that a fibrous filter has depth, whereas a membrane filter is flat. I mean, it is basically a flat surface, whereas in a fibrous filter it is basically a fiber bed. It has certain depth, and because of that it is interesting that as time progresses the filtration efficiency actually increases. The reason for this is, of course, the filtered material adds to the depth of the bed, and therefore the filter, with the passage of time, the filtration efficiency keeps increasing. However, the downside is so does pressure drop. So eventually you do have to clean out the fiber material and reuse it, but whereas in the case of a membrane filter, clearly as time increases, efficiency will decrease, because a membrane filter is a flat surface. It only has so many discrete holes on it. So once the holes are occluded, further filtration is not possible. So the efficiency will clearly drop. Okay, a fibrous filter is primarily used for gases, whereas membrane filters can be used for gases and liquids. Again, the reason is obvious. I mean, if you pass a liquid through a fibrous bed, the fiber can be wetted, can be dissolved. So the fiber itself can become a contaminant in the liquid that you are passing through. So a fiber filter is much better suited to filtration of gases, whereas a membrane filter can clearly be used for either gases or liquids. How about flow rate? A fibrous filter can handle a high flow rate, whereas membrane filter can only handle a low flow rate, and because of that the efficiency itself, the actual magnitude of a fibrous filter is low compared to a membrane filter. A membrane filter is also referred to sometimes as an absolute filter. If you say that this filter can filter down to 0.5 microns, it will absolutely filter down to 0.5 microns. It won't let anything go through that is larger than 0.5 microns, whereas a fiber filter is actually more based on probability and statistics. You have designed it so that it is very likely to capture particles of a certain size range, but you cannot 100% guarantee it. So if you look at pressure drop, which do you think will have a higher pressure drop? Any guesses?
Fibrous.
How many think membrane filters? So yeah, I mean a membrane filter, because it has a high efficiency, a low flow rate, it also tends to develop a higher pressure drop very quickly. All it takes is that you only have one layer of holes, right? Once they get filled, the pressure drop can quickly go up to infinity. So the pressure drop here is low and here it is high. A fibrous filter can be used, I mentioned that there are two purposes, analysis and purification. Can a fibrous filter be used for both purposes or only for one? You cannot use it for analysis, right, because it's a fibrous mess, and once a particle goes in there you cannot see it anymore. For analysis, the important thing is the particle has to be in a presentable form so that your analytical equipment can actually see it and analyze it. So a fibrous filter can only be used for purification, whereas a membrane filter can be used for analysis as well as purification. How about the mechanism of filtration? What is the primary mechanism in a fibrous filter? Okay, see a fibrous filter has depth, so it has pathways, right, and they are very tortuous. What are you relying upon? You are relying upon the fact that particles have a long residence time inside the filter bed, so that they can be captured eventually. So one of the key characteristics of a fibrous filter is residence times are long. In a membrane filter, the residence time, in other words the passage through the filter time, is virtually zero, because it's a one dimensional object, there is no depth to it. So you can in principle say residence time is 0, and the reason that residence time is long is because of tortuous pathways. whereas here there is no pathway. Particle comes, sees the face of the membrane, sticks, right. Okay, so again going back to mechanisms, which are obviously again important in the context of the earlier lectures we have had in this course. What would be the primary mechanisms that apply in a fibrous filter versus a membrane filter? Diffusion is a principal mechanism, because that is really what you are relying upon to give you the capture efficiency. You are expecting the particles to diffuse around inside this filter medium until they get captured. You can also induce charge in the fibers, you can use charged fibers. So, you can use electrostatic effects to some extent. Interception is possible. Again the difference between interception and impaction. So, if you have a fiber that looks like this, interception happens because particles are flowing parallel to it, and a particle comes close enough to the fiber that it actually physically encounters the fiber during its flow and thereby sticks to it. That is what we call an interception mechanism. Impaction on the other hand implies normal impact and capture through inertial mechanisms. In a filter bed that is very unlikely to happen, because the particles are never going to have a sufficiently high normal incident velocity, they are going to have high tangential velocities. So, impaction is virtually absent as a mechanism in a fibrous filter, whereas in a membrane filter the key mechanisms are sieving, interception and impaction. Sieving, because the way filtration happens in a membrane filter is that you have a surface with holes in it. Particles approach, and if there is a match between the size of the hole and the size of the particle, it gets captured. So, in principle it is very much like our sieving and screening that we talked about before. So, a membrane filter in one way is the equivalent of a screen. Interception is important because again the mechanism, when a particle goes through the hole, whether it gets stuck in the hole or not depends on whether it actually contacts the outer periphery of the hole or the inner periphery of the hole. So, interception is another mechanism. Impaction is important because particles in a membrane filter will typically approach vertically in a normal direction, okay. And so, these are the three dominant mechanisms. So, what does that, so what does this tell you in a way? In any process, filtration is not done in a single stage. Why is that? Why do you think people do not do single stage filtration? Any ideas? Let us see who has the ability to think practically. Suppose you are trying to filter a liquid, water to use in your process. Why couldn't you just use a single stage filter and use the water?
All the holes will be clogged with a bigger pump.
Yeah, basically the pressure drop will increase very rapidly, right. So, typically in any process there is a, first it goes through what is known as a, well actually initially goes through a coarse filter which removes rocks and pebbles. Then it goes through a pre-filter and then goes through a final filter. Of the two, the fibrous filter and the membrane filter, which do you think is more likely to be a pre-filter? How many think fibrous? How many think membrane? Now, fibrous filter is the pre-filter of choice. The reason? Well, a lot of these reasons of course, but one of the the low efficiency is one of the reasons. You do not want your final filter to be a low efficiency filter, it has to be the highest efficiency filter. But more importantly, a fibrous filter is more suited to being a pre-filter because it can shed, the fibers themselves can come off and become impurities. So, you need a subsequent downstream filter to filter out material that is getting released from the filter. Now, fibrous filters are actually pretty dirty when you look at them, the way they are made and the way they work. There is always a chance that both fibers as well as even chemical materials can be released and be transported along with the effluent that is coming downstream. So, you do not want to use a fiber filter as your final filter. It is very, very risky, especially if you have a product or process that is extremely sensitive to contamination or impurities. A membrane filter is much better suited to being a final filter. So, the assumption is as the fluid goes through this process, much of the heavy material is removed in the first stage, the medium sized material in the second stage. So, the final filter, which is a membrane, is only presented with a reasonably pure liquid to start with, because a membrane filter is not designed to handle very dirty fluids. It requires fairly high level of cleanliness to begin with. Okay. Okay, now how are these filters made? Because the way that the filter is made also has a bearing on how you use it in the process. So, if you look at how a fibrous filter is made, the process itself is kind of a dirty process. You basically take, by the way, the material, fibrous filters are made of paper, whereas membrane filters are made of polymer. So, as you can imagine, the chances of being dirty are much greater for fibrous filter compared to a membrane filter. So, so to make a fibrous filter, you basically take the byproducts of paper manufacturing, dissolve in a solvent, and you run it or flow it on a screen with perforations on it, and then you evaporate the solvent. So, as you do that, what you will form is a thin sheet that has porosities in it. So, that is the way fibrous filters are manufactured. They are made in sheet form, they are stacked as rolls, they are sold as rolls, and they will have a void fraction of about 10%, a porosity of about 10% as manufactured. So, in this process, as you can imagine, cleanliness is not a major criterion, right. Whereas, if you look at how membranes are made, first thing you start with polymers, which are by definition much cleaner than paper and paper products that you use for the fibrous filters. There are three different types of membrane filters. First is a cast membrane filter, the second is a nuclear pore, third is a Gore-Tex. Now, these are actually trademark names. Nuclear pore filters are made by a company called Millipore, and Gore-Tex filters are made by a company called WL Gore. A cast membrane filter is sort of like a paper filter, except that you use a polymer. You dissolve the polymer in a solvent, cast it in a sheet, and dry the solvent until it develops porosities. So, in many ways, a cast membrane filter is not too dissimilar from a fibrous filter in terms of its appearance, except that since you start with polymer, it is much cleaner. In a nuclear pore filter, the process that is used is quite different. It is a much more controlled surface. So, what you do in this case is you start with polycarbonate as the polymer, you expose it to nuclear radiation. By the way, before I forget, this part of this discussion on filtration is in my NPTEL course on particle characterization. It is one of the lectures towards the end called filtration, so you can look for it. So, the nuclear pore filter is made by taking polycarbonate, exposing it to nuclear radiation, inspecting where the damaged sites are, and actually etching holes at the damaged sites. And interestingly enough, when you do it this way, you get a very, very uniform distribution of holes, both in terms of spacing of the holes as well as the size of the holes. The Gore-Tex filter is made of Teflon, and the way you make it is you take a film of Teflon and you keep stretching it until it just snaps at certain places and develops porosities. So, the goat Tex filter is not as well controlled and as uniform in the distribution and the size of the holes as a nuclear pore filter, but it is an even cleaner material. As you know, we have discussed this before, Teflon is a low surface energy material. So, it is an excellent medium for repelling particles, so it is very easy to keep it clean. So, the goat Tex filter is used where your application demands extremely high levels of purity. So, these are the most commonly used membrane filters. A membrane filter can be made all the way down to nano sizes. There are nano filters available in the market. Again, you do not want to use a nano filter as a standalone filter. Typically, the final filter usually will filter down to microns, and then you would have another final filter that filters down to submicrons, and then you will have a nano filter. So, if you are trying to achieve nano level cleanliness, you need minimum of 5 to 6 stages of purification, because in addition to this, all of this will only take care of particles. As you know, there are also chemical contaminants. So, if you also worried about that, then you need to have chemical filters. Activated charcoal is one way to absorb hydrocarbons, UV radiation is another way. So, this will be supplemented with filters for chemical impurities as well. Again, the thing you have to worry about in nanofiltration is that even with multiple stages of filtration, a nano filter would need to be replaced quite frequently, because even the base pure water or whatever you are using will have a fairly large amount of nano materials in it. So, it is a high cost operation, and you really only want to do it when the process demands, when you have to have separation of nanoparticles from the other materials. In fact, the cost of filtration, if you plot dP versus cost of filtration, it kind of, as the particle size decreases, the cost initially, of course there is I mean, you can look at it kind of this way, dP small cost. So, as you go to larger sizes, the cost decreases, but then as you start approaching submicrons to nano sizes, the cost will start escalating quite rapidly. So, you have to be, and also your capacity will keep decreasing. The amount of fluid that you can pass through a nano filter is going to be much smaller than the amount of fluid you can process through larger filters. So, that also there are pressure drop issues, there are capacity issues or throughput issues, and there are cost issues, which is why nanoparticle synthesis is not a cheap business to get into. Okay, now just like we defined effectiveness of a screen, we also have to define the efficiency of a filter. So, how do you do that? The efficiency of a membrane filter is actually not too difficult to calculate, right? It's for a membrane filter, you can define efficiency actually you can do this on the basis of discussions we have had earlier in this course. Any suggestions on how you would define the efficiency of a membrane filter? Suppose you were asked to come up with an algorithm for, is there something we have discussed before that has a bearing on this? A simplest way to look at it is, it's the amount retained, you can look at it as mass retained to mass flowing past, or what's the term we used for this earlier, it's a capture efficiency, right. So, the efficiency of a membrane filter is simply the capture efficiency of the filter. Of course, you can do this by size, you can look at filter efficiency for various size ranges and so on, but essentially it is a simple characteristic. You know how much material you are passing over the filter, and you know how much is getting retained. So, that gives you the capture efficiency, but it is not so simple when you talk about a filter bed, because in that case the efficiency of capture of a single filter or a single fiber is one thing, but the overall capture efficiency of the filter is going to be a summation of the filtration efficiencies of single fibers, right. So, in the case of a fibrous filter, it is related to the capture efficiency of a single fiber, but through a formula which goes as exponential of 1 minus s times eta s, where eta s is the capture efficiency of a single fiber. S, what do you think S will represent? Any idea? S represents the fiber area per filter area. It is a representation of how well packed the filter is, how much void fraction there is. So, obviously S has to be a function of volume fraction, right, volume fraction of fiber, which is also known as packing density. The higher the volume fraction, the higher the value of S. So, if you look at this expression, if S is 1, eta S is also 1, then the overall filter efficiency is also 1. This expression S as a function of phi can actually be written as phi times 4L by pi df. The derivation of this expression, by the way, is in that lecture. It is basically just looking at the specific surface area of a fiber. L is the depth of the bed, it is the depth or length of the filter bed, and df is the diameter of a single fiber. So, what does this expression tell you? As the volume fraction of fiber material increases, obviously the filtration efficiency increases. As the length of the bed or the depth of the bed increases, filtration efficiency increases. As the diameter of a fiber decreases, filtration efficiency increases. So, if you can make a filter with extremely fine fibers, the capture efficiency tends to be extremely high. So, this is another reason why nanofibers are now being used, particularly in nano filters. In order to be able to filter nanoparticles with high efficiency, you need fibrous filters that have nano sizes. And by the way, for capturing nanoparticles, fibrous filters do better than membrane filters, which is kind of a contradiction to what I said in general, that membrane filters are more efficient. But when you think about the mechanisms that are involved, as we have discussed before, nanoparticles primarily move around by diffusion. So, if you are trying to filter out nanoparticles, you are better off using fiber filters, but you have to make sure that the fibers that you use in your filter are extremely fine or nano dimensional in their diameter. Okay. Now, this is good, but then again you have to worry about pressure drop, right. So, if you look at pressure drop in a membrane filter, sorry, in a fibrous filter, it is related to drag force, because pressure drop occurs because there is a drag that is being associated as particles flow past the filtration media. It is actually also related to LF, not DF, but LF, which is the specific length of a fiber. Which is defined as length of fiber per unit area of fibrous material in the filter. So, the pressure drop depends on the length of the fiber, the filtration efficiency depends on the diameter of the fiber. So, ideally what do you want? You want extremely short fibers which are also have very small diameters, because you want to keep the pressure drop as low as possible while maintaining a high value for the filtration efficiency. The drag force itself is a constant times viscosity times U0. This K, by the way, also depends on the volume fraction of fibers, the constant that is used in the drag force expression. U0 is what we call the phase velocity. It is the flow rate of the fluid divided by surface area of the filter. It is also known as the approach velocity or the uniform velocity, just different names for it. But so again, if you look at this expression, if you want to minimize pressure drop, what do you want? You want actually you want a low value of the packing fraction, you want a low value of the fiber volume fraction, but then that will decrease efficiency. So, one of the things you will notice is that everything that you can do to improve filtration efficiency actually has the effect of dragging down or actually increasing the pressure drop. For example, U0 basically says as you increase your flow rate, pressure drop increases. What will that do for filtration efficiency? If you increase the, just hang on a second, I do not know if you are still taping or not. Okay, we will keep going. So, if you increase the velocity, pressure drop increases. What is it going to do for the filtration efficiency? In the case of a membrane filter, it will increase your filtration efficiency because it increases your impaction velocity and therefore it increases the Stokes number. In the case of a fibrous filter, it kind of has the same effect because the velocity, the approach velocity only has an influence up to the first layer of the fiber. Because the velocity will quickly drop to 0 as soon as the gas or liquid, well, the gas encounters the face of the fibrous filter. The rest of the transportation occurs due to diffusional processes. So, in both the case of the membrane filter and the fibrous filter, a higher value of U0 is good from a filtration efficiency viewpoint, but it is not so good from a delta P viewpoint. And obviously viscosity, if you are trying to process more viscous fluids, you do have to encounter a higher pressure drop. Does it have an influence on filtration efficiency? What happens if you have a more viscous fluid compared to a less viscous fluid? Which one will be easier to filter? Less viscous? Actually, it turns out that a more viscous fluid is easier to filter because its flow characteristics tend to be more non-Newtonian. So, we talked about the Stokes number, which is a function of the stopping distance. The particles have a greater possibility of stopping when they are entrained in a viscous fluid compared to a less viscous fluid. So, the point is that filter design, particularly fibrous filter design, is something that has to be done very carefully. You obviously want to maximize filter efficiency, but you have to do so without at the same time compromising pressure drop characteristics. Now, let us look at this. So far we have been kind of talking about this parameter S and the delta P parameter. How about this eta S? Well, eta S, which is the single fiber collection efficiency, in many ways is similar to the collection efficiency of a membrane filter. However, there are more mechanisms involved in the case of a fibrous filter, and so the filter efficiency has to be defined in terms of more than just this expression assumes that transport is dominated by convection and impaction, whereas in the case of a fibrous filter, as we have seen before, diffusion is also an important mechanism along with interception. So, there are actually two dimensionless parameters that have an influence on that parameter eta s. Eta s is a function of two parameters Pe and R, where Pe is called the Peclet number and R is called the retention number. Peclet number is a measure of diffusivity or diffusional collection, and the retention number is a measure of interception. The Peclet number is expressed, they are both dimensionless parameters. The Peclet number is a multiplication of a characteristic velocity times a characteristic length divided by a diffusivity. So, if you take the local velocity of the fluid that is approaching a fiber multiplied by the diameter of the fiber and you divide it by the Brownian diffusivity of the particle, that gives you Peclet number. The retention number is ratio of dP over dF. So, it is a ratio of if you have a particle that is approaching a fiber, the diameter of the particle is dP, the diameter of the fiber is dF. The ratio of dP to dF is called the retention number. So, these are the two important dimensional numbers that dictate the collection efficiency or filtration efficiency of a single fiber. And in fact, the expression is eta s equals some K1 times Peclet number to the power minus 0.67 plus K2 times R squared by R plus 1. So, for a given transport situation, you can calculate your Peclet number, you can calculate your interception or retention number, and you can estimate the overall efficiency of a single fiber, which is in this expression. You can calculate the value of S, and thereby you can calculate the efficiency of the fibrous filter overall. The typical value of, for example, this has two components and you can kind of split them into a diffusional component, eta s diffusional and eta s interception, and the overall efficiency is a sum of the two, which basically says that there is very little interference between the two phenomena. Most of the submicron particles, nano dimensional particles will be collected through a diffusional process that is expressed by the Peclet number, whereas most of the particles that are in the micron and larger range will primarily be captured through interception as a phenomenon, and it will be through this expression. So, for a given particle size distribution, you can pretty easily estimate what is going to be your diffusional capture efficiency and what is going to be your interceptional capture efficiency. And how do you use that kind of knowledge? It depends on your application. For example, if your process is particularly sensitive to particles that are a micron and larger, then you want to maximize this part, even if that means you sacrifice some in this range. And similarly, if it is the other way around, you design your filter in such a way that you maximize this capture efficiency even if it means you are losing out a little bit on the interception side. So, all of these are design considerations for filters, and we have talked about some of the differences between membrane filters and fibrous filters and so on. One of the challenges in selecting a fiber system or purchasing a filtration system is how do you certify it, how do you validate it. Are there standards that you can pick up on that you can use to evaluate a filter with respect to its performance. And it turns out that there are various standards that have been established for ranking filters, and the organization that is most active in ranking or rating of filters is called ASHRAE, which stands for American Society for Heating, Refrigeration and Air Exchangers. This professional organization has the responsibility for setting standards for filters. They specify methods for testing filters, and they also specify the criteria that the filters have to meet in order for them to be used in the process. In the next lecture, we will talk a little bit more about how filters are tested and ranked, and then we will talk about industrial filters in more detail. Okay? Any questions? Okay, see you tomorrow.